I can do that. I can do that.
First, make sure this is prompt.
Okay. Okay, so I have the pleasure duty to continue a little bit more in actually introduce Dan Crawford. As said in the beginning, in the morning he was ill, but really very happy that he moved, and that was his several contributions to high accuracy quantum mechanical properties of chiral molecules. He's chair of chemistry science, Blacksburg, Virginia. Game is with software developers all over the USA.
Hear me clearly? Good. Perfect. First of all, I want to thank the organizers for the kind invitation to come to this wonderful meeting and give you an idea of what we've been working on in the Molecular Sciences Software Institute. I don't know what I need to do to switch it over. There we go. All right, so the MOLSI, as we call it, the Molecular Sciences Software Institute, is really intended to be a service to the global computational molecular sciences community. And I'll give you some idea of what I mean by that as we get into the weeds, but I want to kind of motivate what really was the establishment, the founding of this institute, and tell you a bit about it. So computational molecular sciences, first of all, this is a very broad field. For everyone who does computation in this room, it probably encompasses most of you, but we would consider quantum chemistry, which is my particular subdomain, as well as bio and macromolecular simulation and computational materials science, anything that deals with the molecular level chemistry and physics. And the history of this field, as so many of you know, really reaches back many decades to the very dawn of computational science itself. And over that time, we've become a full partner with Experiment. We directly engage with experimentalists and provide a lot of predictions and new developments for experimentalists sometimes to follow, including domains, in development of new drugs, elucidation of functionalities of biomacromolecules, development of more advanced materials for solar energy storage. This is probably an audience that I don't have to convince that this is an important field of science. Central to all of the work the field of computational molecular science does is a set of community software codes, program packages, mostly developed within academic communities, at least initially, and some moving into commercialization, depending. But there's a huge number of these, and these are all of the MOLSI's community code partners so far. So we have about 40. And I've tried to partition these up into material science in the upper left, biomolecular simulation on the right, and quantum chemistry on the bottom. But of course, they don't partition perfectly. Some appear in different categories at the same time. But these really are the central tools. These are what enable us to do the new science that we do as a community. And so we have a lot of challenges. And the first challenge I want to bring up is our code complexity and the historical legacy of the field. Right now, computational molecular sciences programs can contain literally millions of lines of handwritten code. And in aggregate, across the field, this really is hundreds of programmers who must develop and maintain this code and contribute new stuff to it. There's a gigantic language diversity, huge. All of your favorite variants of Fortran can be found there. C, every new standard of C++. You can get into scripting languages such as Python, Perl, etc. I do worry that there might be individual code packages that have all of these at the same time, but I really hope not. I hope it's more limited than that. But there's also an incredible algorithmic diversity. Basically, every algorithmic paradigm that exists, you can find it in some of our codes. Because we're not just trying to solve one problem, we're trying to solve a range of problems. And these packages have really evolved ad hoc manner over many decades. Some are brand new, but some are many, many decades old. And the reason for this sort of ad hoc development is because the problems that we're trying to solve are extremely. You don't understand the problem completely until you've already started writing code to try to deal with it. That's where you really begin to understand the depth of the problem, in my opinion. Another challenge has to do with computing hardware, which is changing constantly and sometimes very rapidly, or in terms of architecture. But lots and lots, in fact, the vast majority of computational molecular sciences codes are really developed with no great vision for parallel task management. There are some wonderful exceptions, but they are exceptions. And it's just going to get more and more difficult for us with reduced power solutions. Checkpointing is going to become extremely important. You're going to have specialized hardware, et cetera, that we need to try to take advantage of. But it's very difficult to pivot and really change when so much of the fundamental algorithmic architecture depends on what the hardware architecture is that you're deploying on. And so a lot of codes, especially in the quantum chemistry community, they're really limited to shared memory type systems, not distributed memory systems. And then finally, the third challenge is the educational culture. Now, I can primarily speak for the US, but I know that there are similar challenges all over the world in terms of physics and chemistry. Undergraduate programs in chemistry, in particular physics, they typically require no training in software engineering or programming. We'll have some wonderful students who come through who've gotten a whole bunch of programming experience. They are really valuable to us. We try to grab them. But most students getting a bachelor's degree in chemistry or physics learn very little about programming. And when they get to the graduate program, and most people in the US in chemistry programs go directly from a bachelor's to a master's. When they get to graduate programs, this sort of lack of training in software development is not resolved, right? The students at Virginia Tech, for example, which is my home institution, our best students take maybe 4 or 5 lecture courses total for the PhD. And they're not taking software engineering courses, right? They're taking statistical mechanics, there's spectroscopy, quantum mechanics, etc. So we don't resolve this problem, which means that if we want to train our students how to engage with these gigantic software packages, we have to teach them ourselves. And that means there's a very sort of ad hoc, sort of idiosyncratic education in software engineering for these students. And sometimes, because the people who are teaching them are people like me who are not software engineers, that doesn't mean they always learn the greatest, latest tools and such. Furthermore, there's a question of credit. Credit is usually determined in the scientific community based on peer-reviewed publications. And building something like a software package that can facilitate a lot of new science and therefore new peer-reviewed publications, students rarely get credit for that. So that's another challenge. So it's very natural that students and postdocs would have a sort of just get the physics working kind of approach. And as soon as you've got it working, publish your paper and move on. And so the code that they write, so much of it is just gone, right? It doesn't have a lifetime beyond the student itself. So this is where the MOLSI comes in. These are the reasons for our existence, is to try to tackle these challenges. We launched just over 8 years ago, August 1st, 2016. We were funded principally by the U.S. National Science Foundation. It's a collaborative effort. The headquarters of the MOLSI are at Virginia Tech, but it's really a collaborative effort among 9 different institutions, including Rice, Stony Brook, UC Berkeley, Rutgers, Southern Cal, Cal Poly San Luis Obispo, Iowa State, and the University of Michigan. And that's basically where my board of directors, all of those different institutions, are where they reside. And it was part of the NSF's commitment to the White House's National Strategic Computing Initiative in 2016. And it's been funded by multiple components. We had a first phase, which is the first 5 years, and then we were renewed in 2021 for our second 5-year phase. And we're supported by a broad range of divisions and directorates within the National Science Foundation because our impact is intended to be not just chemistry, not just physics, but well into biology and others. And the fundamental purpose of the MOLSI, as I state here, is to serve and enhance the software development efforts of the field of computational molecular science. There's naturally a U.S. focus because of the funding, but we consider this to be a global effort, if at all possible. So again, the MOLSI headquarters in Virginia Tech Corporate Research Center, about a 7,000 square foot space. It's really lovely. If you come into the U.S. and can find your way to Blacksburg, we'd love to show you around. So that's an open invitation. So who is the MOLSI? Several different components, the people who make up this organization. At the heart of the MOLSI are our software scientists. Right now we have 9 on board. We've been as high as 13. There are natural fluctuations in this. These are really software engineering experts. Most of them are coming from the computational molecular sciences, but some come from computer science and applied mathematics, for example. And then there's our software fellows. This is a group of, really a cohort of graduate students, PhD students, and postdocs that we support all across the US. And I think we're up to more than 120 students and postdocs that we've funded so far through this fellowship program. And they're selected by our external advisory board, and they are mentored by our software scientists. Our board of directors, that's the third component. These are the 9 PIs. I'm one of them. I showed you some of the others on the previous slide. And they provide guidance for the direction of the MOLSI overall so that we can identify our highest priority efforts. There's our advisory board, the Science and Software Advisory Board. But most of them come from academia, but some from industry, some from abroad, again, to help us set priorities. And then finally, there's the large number, about 40, of community code partners. So developers and users of these various codes who work with us to make sure that the needs of the community are met by these codes, if at all possible. So we have 3 goals in the MOLSI. 3 goals. The first is to provide expertise and infrastructure. So my software scientist team at the MOLSI is working on a lot of software infrastructure for immediate use, we hope, by the broader computational molecular sciences community. I'll show you some of what those things are in just a minute. But they also provide their expertise. We collaborate with a lot of software developers and even users to try to make sure that we understand what the highest priority needs are, but also to find ways to solve problems of interoperability, sharing data, etc., between these different codes. We don't just work on a single code. That's not our goal. We work with multiple codes to try to enable them to share each other's capabilities and to share data between these codes. Interoperability is a major theme with this. We also provide education. The MOLSI's education initiative has grown, frankly, to be much larger than I expected it was going to. It's really, I'll give you some data on this a little bit, but we organize summer schools and education workshops, reaching all the way down to the high school level, and lots of training programs and online resources that everyone who's interested has access to these things. We don't limit it at all. And then we reach really beyond the traditional sort of chemistry and physics domains to try to interact with computer scientists so that they can learn what it is we do, and that better enables them to collaborate with us going forward. And then finally, our third goal is to provide community engagement and leadership. One of the difficulties with sharing data, for example, between software packages is that nobody agrees on what the best standard is. And so we need to try to develop these standards. Now, the problem is that we can't, at the MOLSI or anybody else, you can't basically declare a standard, give it to everyone, and expect them to accept it. Because when it comes to academics, the fastest way to get them to ignore you is to tell them what to do. So we don't do that, right? We try to bring them together in certain domains, facilitate discussion, help them find common ground as to what they really need, and develop standards in a grassroots type of approach. Okay, there's a lot of text on this. I'm sorry for that, but this is basically a highlight of some of the things that we've been doing. We've got 9 software scientists on our team, as I mentioned. We've held more than 37 workshops, software workshops with the participants. These are both domestic and international workshops. We've had quite a few internationally. We have a lot of cyber infrastructure that I'll mention. Some here may be familiar with the basis set exchange. I'll show you a bit more about that in a moment. But we also have the QC archive project, the MOLSI driver interface, and a lot more going on. In our education program, we've had face-to-face instruction with more than 3,000 students through this program, and another 5,000 students work through our online curricula each month. So again, this is open to everybody, so I encourage you to take a look at it. You'll hear more in a minute. We currently have 8 software fellows supported, and we've had a total of 124 graduate students and PhD students in the program up to date. And then the whole team has published more than 160 papers, 8,900 citations, and so on since 2018. Our software scientists, I just want to show you a few of them. Our lead software scientist is Dr. Paul Sachs. Paul has experience across the entire domain of computational molecular science, so he's really been engaged in all of it. I'll highlight Taylor Barnes, who got his PhD from Caltech. His focus is on quantum chemistry and also quantum models within material science. And then Jing Chen, who got her PhD at North Carolina State in molecular dynamics and computer science. Sam Ellis is a bona fide computer scientist. Sina Mustafanejad, who got his PhD at Florida State, is our AI ML expert on the MOLSI. Jessica Nash is our education lead. She also leads one of our central software infrastructure projects that I'll mention. And then finally, Ben Pritchard, who got his PhD from Buffalo in quantum chemistry. He's our deputy lead software scientist. He has led the basis set exchange, the QC archive project, and more. So he's one of our most effective team members. So what are these infrastructure projects? I mentioned the basis set exchange. That one's probably the highest immediate impact from when we launched it. The QC archive is another one that I'll say something about in a minute. This is designed for high throughput quantum chemical calculations to provide data, curated data, carefully curated and standardized data for all sorts of applications that I'll mention shortly. The MOLSI SEAM project, that's simulation environment for atomistic and molecular modeling. The MOLSI driver interface here, you can see we like to use our logo for a lot of different things. So the logo appears in a lot of these different packages. That's an interoperability focused package, right, where you have different codes that can drive each other towards specific goals. Okay, first the basis set exchange. We launched this in 2019. The basis set exchange was originally controlled by Pacific Northwest National Labs in the US. But with lack of focus and funding and personnel, it had sort of fallen by the wayside. This is an extremely important resource for the quantum chemistry community. It focuses on Gaussian type basis sets. And we took it over and relaunched it, a complete redesign, made the thing completely open source so that, and with a workflow that people can actually contribute new basis sets and corrections. And we get about 10,000 website users and about 50,000 interactions with this each month. And so basically, almost every quantum chemistry code draws their basis sets directly from the basis set exchange. And we published a paper on this in 2019 in the Journal of Chemical Information and Modeling. I make a point that I'm the director of the institute, but I don't put my name on a paper unless I've made a significant intellectual contribution to it. I think this is a good rule. I really wish I had made a significant intellectual contribution to this paper, because in no time it got, I mean, it's approaching 2,000 citations just like that. It's a very high impact piece of work. QC archive I mentioned before. This is for high throughput quantum chemical calculations. It's really a larger ecosystem. QC archive has a lot of subcomponents to it, all designed to streamline setting up and carrying out huge numbers of quantum chemical calculations on whatever computing hardware you have. You can get your own version of this software and install it yourselves and use it for your own purposes. We maintain a publicly facing database resulting from this that is based on a standard that we've worked with the community to develop called the QC schema. And again, it's an open community database with hundreds of millions of calculations in it. This past April, we did 17 million calculations in that single month. We ran 1.7 million in a single day. So that's sort of our record so far. We'll keep working on that. I mentioned the simulation environment for atomistic and molecular modeling. This is one of two of our packages, our infrastructure projects, that are focused on interoperability, helping codes use each other's capabilities and sharing data between them. SEAM is intended to be a very lightweight Python-based infrastructure, so that it's pulling data from different output files. And users, what's really lovely about SEAM is that users can actually, through a graphical interface, literally drag and drop code infrastructure into a workflow and build your own customized workflow with it using a wide range of packages, some of which are on the right-hand side. And then there's the MOLSI driver interface. This is another interoperability focused package, but whereas SEAM doesn't touch any of the actual codes that serve as engines underneath it, MDI, the MOLSI driver interface, goes directly into, we make changes to the code and compile them in together. So this is more of a lower level sort of sockets based communication between packages. Very heavily on MPI, but it's got our own type of protocol based on the MDI protocol, and we can do a lot of different things. We have lots of different drivers and computing engines within it. For doing QMMM, you can do ab initio MD using LAMPs or others. And yeah, a wide range of proof of concept, and we keep getting more and more contributions to it and adding new engines to it all the time. I think I'm going to skip our COVID-19 molecular structure and therapeutics hub. We launched this in March of 2020, and this was a point where biomolecular simulation teams could share data very, very rapidly. We were very proud of what that was. I'll also skip the MOPAC project. I'll say something about our education project. As I said, it's grown to be a lot larger than I ever expected it to be. But it's also quite global, so we have a wide range of people accessing our educational materials. You can get to these at education.mulsi.org. I encourage you to take a look at that. And we've got a huge number of partners that make use of this. We did a series of workshops, customized workshops for the Pfizer Corporation, for example, and others. And so we have workshops all over the U.S. and even especially in Europe. We've had a number of them. So again, it's really a global effort. Our fellowship program I mentioned before, we have fellows all over the U.S., 124 so far supported in this program. And they go off to lots and lots of positions in academia, industry, national labs. It really is a good stepping stone for them. And to put faces with these are some of our software fellows running back all the way to 2017 when we first launched this program. So it's been moving along quite well. I got this email from Alex Holhouse, who's an assistant professor at the Washington University School of Medicine in St. Louis. He was one of our software fellows from a number of years ago, and he sent me this lovely email that I just like to think about sometimes, where he said that his entire lab's ecosystem is built on the principles, tools, and approaches that he learned through the MULSI. That's the kind of impact that we really want to have, but on a very large scale, if at all possible. This is my board of directors. Cecilia Clementi is our co-director for international engagement, so she's in Berlin. Robert Harrison at Stony Brook is the co-director for parallel computing. Teresa Head-Gordon at Berkeley is our co-director for biomolecular simulation. Shantanu Jha, who is at Rutgers, though I think he's moving to Princeton, is co-director for the software engineering process, middleware, and infrastructure. Anna Krylov at USC is the co-director for quantum chemistry. Ashley Ringer McDonald is our co-director for education. Teresa Windus at Iowa State is our deputy director and also co-director for interoperability. And Dominika Zagid at the University of Michigan is our co-director for materials science. This is our advisory board. As I said, most of them come from academia, but we have a number of industry national representatives on this group. We meet with them twice a year. And with all of that, I really want to say not only thank you to you, the audience, for listening, but I also appreciate the larger MULSI community, which I say hundreds here, but it's actually grown to thousands. People who've worked with us to try to enable the MULSI to do a lot of good for the community and to help us do even better as we go forward. So with that, I'll just repeat this text-heavy slide with lots of highlights of what we've done. And I thank you all very much for your attention. I appreciate it.
Thank you very much for this great overview. Questions or comments?
Hi, my name is Mohammad Khatamirat from Technical University of Berlin. First of all, thanks for this amazing presentation. I have two questions. I'll make it short. You mentioned interoperability and you showed a few drivers. Is that limited to tools, or do you have solutions also for data interoperability? And the second question is, you talked about standards and bringing people together.
Yes.
I can imagine that's a challenge and a bottleneck at many corners. How far-reaching would you say are these developed standards?
Those are both excellent questions. So in terms of the data interoperability, I sort of mentioned very quickly that we've helped to develop this data standard called QC schema, and it really is intended to allow different quantum chemistry packages to share data back and forth. And it'll be continually under development. It never has everything that everybody wants, but that's basically the way standards tend to work. But this has been adopted by multiple software packages, and we're trying to make it easier and easier for them to adopt it themselves, even more to adopt it through another system called QC Elemental, or instantiation of the QC schema. The QC archive package makes direct use of that. So every quantum chemistry calculation that goes through the QC archive, when it's stored in our database, meets the QC schema standard. which means that any of those packages out there that use it can immediately take that data in and use it for whatever purpose they have.
So that would mean a lot of ontology development also along the way.
Say again, please.
Also, that includes ontology development along the way, I would assume.
Yes, but ontology hasn't really been as, that fundamental level, quite a large role in the development of the schema. It's a little bit, I don't know, simpler than that in some ways, I guess is the way I'd phrase it. But your second question was what?
Regarding the standards. So you said you bring people together to talk about standards,
Yes.
As opposed to tell them, hey, here's how I think
Yes.
everything should be.
Yes.
So these develop the standards that hopefully community brings
right.
together. How far-reaching are they? Only the people who develop them use them, or you're able to extend them to, I don't know, outer institutes and even industrial partners?
Our focus has really been on the developers of the software, because they're the ones who really need to use the standards for storing their own data for other codes to use, or bringing in data for subsequent calculations. That's sort of the first line that we try. Oh no, it was having the government attacking them and over and over. Really going to talk about later. Yeah,
But in another, a little bit also.
Yes. However, national, and then the White House said that.
Mhm.
Don't do that, me.
I just.
Well, also, well, I to foundation have so to you
On our minds since the day we'll go. NSF pursue. We all. So some action of some of it. For the Department of Energy. They decided to start playing anything.
Overview and for. Daniel.
program. Our first principles intelligence. Show out desire principle. That's two level price. For most to find the fundamental principles. So that is why it's varieties. So come to start. For and here is first principle calculation to the central. First one density function most five ones and the last was by the considerations materials. So that discover even in fact the solid material can use infinite from information for the search condition. Is very time consolidated
and use inputs more works said let's the and the remote we don't know challenge actually very good in complex the main is that you very so very important analysis to that's for example for the unit for to learn natural space学的感觉the deep actions deep 想不通 没有在 deep 他们不一直 the physical response the first Hamiltonian is very key quantity. It depends Hamiltonian as a function from actual repair. Kind of as well. Maximum structures tricky and so happy for one here. That's our problem. We use work to treat this problem. And that's mature Hamilton. Current issue is that the structure is very correct. Is to very happy exam can learn from unstructured. You can see this graph layer. Other dimension, so that's you. So we find a so here gets found. This is actually a proof of principle. Yeah. Also can be done here. One use we provide a depend problem for the first time. And we copy its architecture. And we find mature. That's the accuracy can improve to sub-milliview. And we also extend the method to study magnetic materials, and this allows us to study very complicated magnetic structure and study the influence of magnetism on electronic structure. As you can see here, we start from a flat structure, and we can make prediction on cold nanotube structure, and even very new magnetic structure we can reproduce the band structure quite well. And also we recently generalized the deep learning architecture from Computational DFT to generalized Computational DFT. So this enable us to make a hybrid functional calculation on a very huge system. For example, the magical angle two-spiral graphene. And the lateral generation is to study DFPT, density functional perturbation theory, the electron lattice coupling, and we can do this very laterally by auto differentiation. And so with this, we can bring DFT and DFPT into a unified deep learning framework. We can speed up the electron phonon copying orders of magnitude. So this enables us to study a large system to predict the BCS superconductivity temperature. And recently, this is an important step. We can make deep edge access and also plane wave and DFT Hamiltonian. We can read that Hamiltonian and make transformation onto a time basis. We can predict, preserve the accuracy and change the data to localized basis that can be accessed by deep edge. I think now deep edge can access all the DFT code. That is important for future build for large database. And a recent work that we developed a physics-informed unsupervised learning version like AlphaGo to AlphaGo 0. We have a deep edge and deep edge 0 version that we can coherently integrate DFT algorithm into neural networks. And finally, that is a very amazing progress. We previously only started very simple material systems by perturbation. Now we want to generate to universal material model. Because a lot of people want to, for example, explore the large material model that to predict the relationship between structure and the property, but that is quite complicated. We propose a new strategy to achieve this large material model. First, we need to train a universal model for deep edge, and then you use deep edge to generate data more efficiently and build a large material database to train the large material model. Because of deep edge has a locality property, we can learn from local content on large training gas capability, but there is more evidence. So the outline if you more efficient is intelligent, and so that's the next generation DFT algorithms. And so, as an outlook, I think there's a lot of opportunity for the field for the AI, the DFT plus AI. We can develop an AI-based DFT code, and with this, we can benefit from the database construction improves the neural network performance, and this will speed up the construction for material database. We can consider much larger material database with low cost. So with enough material data, that's enable us to explore the large materials model. And finally, this summary and slides. And our group will aim to develop AI-powered next generation first principle method. There's lots of progresses. There are some review articles. The last one is in Chinese, but you can use, I think you can use ChatGPT to translate into into English. This is a tutorial for example, for undergraduate students and to learn the underlying principle. There will also have a tutorial online, and all this code and data are an open resource. And with this, thank you for your attention.
Right, we can take one or two questions. Yes, Rafi.
Yeah, thank you for that amazing talk and work. So if I understand this right, you are training your neural network to predict the self-consistent DFT Hamiltonian.
Yes.
Right? So I'm wondering where the speed up is coming from. You are eliminating all the pre-SCF steps, and then there must be some additional factor that is leading to orders of magnitude speed up. Can you explain what I'm missing?
This one, right?
Yeah.
So we first to do training calculation, usually about 100 items per supercell, and randomly put the structure. We need to perform roughly 300 training calculations. With this data, we train a neural network and then make a prediction on arbitrary twistor angle case.
Okay.
So after the training is finished, the neural network parameter can be used for study in new structures.
Right. So okay. So after it's trained, it now predicts these for a new case, for a new big system.
Yeah.
It predicts the self-consistent DFT Hamiltonian.
Yes.
And then you still need to solve that.
The eigenvalue problem.
Eigenvalue problem.
That's a good point.
Right. So, okay. So I'm still wondering where the speed up is coming from. Maybe we can talk later.
Okay.
But you understand the question?
We can use the linear scanning algorithm to solve the eigenvalue problem. Now we only need states near the Fermi level. So that's we can go to linear scaling.
Okay.
And it's a sparse matrix.
Right. Okay. Thank you.
One more question.
Okay, very quick question. So you mentioned small structure for the training 100 items, long-range interaction. Some long-range interaction beyond 100 items supercell. Does that affect the construction of a Hamiltonian?
That's a very expert question. In the present, our architecture focuses on locality property. So we simply neglect all the long-range parts.
Okay.
If for some cases long-range parts you want to come back, there are two options. One is you may redesign the neural network architecture to learn both short-range and long-range simultaneously. Another way is if you can add the long-range parts analytically, that would be better, I think.
Okay. Yeah. Thank you for answer.
So let's thank Youngju again.
Thank you, Chairman.
Will display. Hi. So you're right.
About that. Okay, so our next speaker is Jipan Liu, who's an editor along with me, one of my fellow editors at the Journal of Physical Chemistry, and he's going to be telling us about large-scale atomic simulation, application of ethene epoxidation on silver.
Okay, thank you, Daniel. First of all, I thank Liu Yi for a very kind invitation. Actually, I'm mainly working on catalysis, so not really on so much on materials. So today I hopefully give you some information for our work for the program development for the LASP. And this program is mainly for the atomic simulation, particularly for some very complex materials and reactions. So this year we released this software version 3.7. So it takes about more than 6 years for us to arrive today. And basically, this software can be used for the major thing is for global potential surface sampling, and we use our neural network potential training to do this job. And based on this functionality, we have the interface search, the surface structure search, reaction sampling, and also automatic reaction, say pathway sampling, and this is the neural network potential framework. So basically, in today, I will give you some idea how we arrive today for so many different functionalities. I know for many speakers in this audience, they have some experiments for catalysis, because catalysis is a very good example for the real world materials. We can think about this kind of material have some mixture of supporting material like silica and alumina, and then there are some metal species or catalysis, and then there are molecules interaction with these kind of metal particles. The whole system is working at some high temperature, high pressure, and maybe even in solution. So it's a really real world material and real world catalytic systems. So from our theoretical point of view, we need to say convert this kind of chemistry or physical problems into our mathematical problems. So basically, it's a potential surface concept. So most we learn, say, potential surface like this one, very simple initial state and final state with, say, 2 or 3 different transient states. But actually, you should think about the real potential surface like this kind of really rugged and many, many different minimums. And a lot of minimums have very close energies. So in order to search for this kind of potential surface, you need to use our, say, Schrödinger equation solver, basically density function theory kind of calculations, and then use the statistical mechanics to get the distribution of all these states, and eventually you use this statistical sum of this kind of partition function, and you get the thermodynamic quantities, and you give the stability of the minimum, and then use this kind of data, and you can derive the kinetics, for example, transient state. So basically, this is the traditional way from a real-world system to the mathematical, say, system, and then we use this kind of understanding or computational data, and finally we do the experiment to predict the experiment. And the whole procedure is very difficult because the computational loading is very high, and also need a lot of manpower to do these kind of things. So for our, say, for my group, we are thinking the major, say, work we need to do is do this kind of automation and intelligence to make the whole process easier. So the central question is, can we, say, simulate the catalysis under real conditions? So we need to treat the structure complexity under, say, reaction conditions. The whole surface will reconstruct and have many, many different molecules, say, interact with the catalyst. And the second thing is, because the chemical reaction itself, by itself, is very complex. The molecules like CO, carbon monoxide plus with hydrogen, it can goes to Fischer-Tropsch synthesis, goes to carbon 2, carbon 3, and different molecules. And the prediction of the chemical reaction, we know it's a rare event. It's very, very difficult. So my group have been working in this field for many, many years. So basically, we use some traditional software like car step when I was in UK, and then we also move on to Siesta to make the calculation fast, and also did a lot of calculation using WASP. But all this software people are using as us, you will find some functionality are very difficult to be implemented for the catalysis problems. Particularly, you want to search a structure very fast and do the calculation very large. And this becomes our main driving force to develop our own code to make these things to happen quickly. So first thing is we have our software called a methodology called SSW method. We developed in 2013, and then we have our generalized, say, global neural network potential in 2017, and then we developed our software called LASP. So the basic framework is very simple, as most you have heard by nowadays, people trying to replace DFT calculations using a neural network potential to convert the structures into some, say, energy and kinetics. The problem is, if you do the traditional way, the prediction power for this kind of neural network potential is very weak, because the extrapolation power for the neural network potential is not as good as us expected. So this is why we add a G in our neural network potential, because we use our global data set. And for the last 6 years, we have generated more than 300 different potentials, and we can simulate a very complex material up to 7 or 8 elements, and we can do many different elementary reactions. So this code has now been used by thousands of researchers across the world, and in the just 2 or 3 years days, they have published a lot of papers. All these papers are published by community, it's not by our group. They have some work in Nature and Science, and also JAX and Chemie. And also a lot of Chinese, say, institute buy our code. They try to incorporate with us to develop some functionality, so they become the commercial users. So we use our code. I just give you an overview for this code, what we can do for this kind of code. We can search the global Peninsula surface for very complex material like this kind of zinc, chromium, oxygen, because the chromium has a different oxidation state. When you do catalysis, you typically mix with zinc, with chromium oxide, and then you didn't know what's really going on with the oxidation state and the composition, but using our code, we can identify this real composition of the catalyst. And we can also do very complex chemical reactions and Fischer-Tropsch synthesis, and also machine learning for some copper-zinc catalysis. And use this code, we can also do some semiconducting material. For example, this is a FINT we know very well in the computer. So basically, we want to understand when the silicon was oxidized into silicon oxide, so what's really going on for the interface? But this is difficult information can be obtained from experiment. So using our code, we can use our machine learning based global search to search all this interface between silicon and silicon oxide. And eventually we got a paper published in PRL to suggest a new interface between silicon and silicon oxide, which should give you a good performance to minimize the quantum tunneling effect. And use our code, we can also step by step to design experiment. This is the dream for us, for our group, for many years. So for example, in this case is palladium silver system. We have first of all palladium 101. This is this is a very typical system. From theoretical calculation, we start from some flat, idealized surfaces and do the calculation to gain some understandings. So this is the first stage. And then we from this one understanding, we start to mix with other metals to silver to identify the active site. And then we add the support, and finally we predict this one should be a good support. And finally we do experiment to make these things happen. And eventually we identify very good catalyst to selectively to convert acetylene to the ethylene. And use this kind of fast calculation, you can also build a large database with a very easy, say 1 person or 2 person. So for example, this is a very say general question in organic chemistry, people actually build a lot of phosphorine ligand into the metals, and in this case we constructed many different ligands and assemble this kind of ligand into the palladium center and use our code to fast calculate the energetics and build a larger database. The database is still growing. This can be done automatically. You use the AI model to generate this kind of ligand and put into different metal, and eventually we get the energetic descriptor to describe the bonding strengths between the ligand and the metal. And use this one, you can imagine, we can design experiment. For example, if you want to have this reaction to occur, but you didn't know the ligand, what is the best ligand to promote this reaction to occur? And use our method, we predict about 17 different ligands should give you the ideal production. And then we ask experimentalists to do the experiment, and finally we identify 3, and one of them is really cheap. So this is the purpose we try to realize in our lab. So to speed up the finding in the experiment for chemical reactions. So after all these applications, I want to give you some information. So why LASP program can do all this different stuff with good efficiency and good accuracy. What I want to stress is the data set. Because nowadays we know the large language model is based on the larger data set, which is the human accumulated knowledge from the history. And if we want to do the material simulation, we actually need something like a good data set. Here I give you some very simplified illustration. So what's the global potential surface should look like? So this is a very simple data set we call MD17, which comes from the molecular dynamic trajectory of molecules. And if you plot this kind of a trajectory into this kind of graph, you will see under the order parameter L equal to 2, you have only a small point in this kind of, say, diagram. That indicates this kind of data set is strongly localized into the vibration of the molecules. And then you go to some like a QM9, which is a quantum mechanical data set from 9 heavy atoms molecules. And if you plot in this same graph, and you will see this one grow larger. This is because this one has many molecules, like ethylene and also benzene, and then give you a large area of this one. But if you see our data set, you will find this data set is completely larger compared to this kind of small set. And in particular, there's many high energy stuff and also the melted stuff in our data set. So we call this as a global data set. Using the global set, you can identify chemical reactions, identify unknown, say, molecules and structures. So from the years, this is also the initiative for the material genome. People have accumulated a large data from our simulations, from the reactions, from the clusters, from some bulk materials, from the catalysis. We have many data from different groups, from different area of the world. So if we can have a model to learn this so-called global potential surface, have many elements, have many different size of material, this should give us a real powerful, robust, say, potential surface. So this is our original purpose. So can we do this? So we have found that this can be done. If we do this kind of a larger scale simulation using SAW to sample the data and use our program to simulate or train all this data, we should be able to finally get a very robust potential surface. So this is the framework for our code. Because this code is written by ourselves, we write all this code in Fortran. And initially, we start from the Bella Panello, very simple scheme. And finally, we found that scheme is not good enough because it's too simple for the descriptor and also too simple for the long-range interaction and also such local interactions. So we propose a many-body function corrected global potential surface. We call the say global many-body neural net. And with this, we have actual layer of many-body function here to enhance the functionality for this potential surface. So all these methods developed through the years. So I have been in Fudan for about 20 years since I came back from, say, Britain, and many of this has been, say encoded in our code. So first, I want to give you some idea for SSW method. So this is the key for the global machine. And here I list a lot of famous names in this field. We call the structure prediction method, and including this kind of umbrella sampling, although it's not a really structure prediction, but you can consider it's a really basic. You add the bias to promote the structure. And then you have this kind of metadynamics, Bayesian hopping, David Wells, very famous name. And in Uzbek, which we know Organov did a lot of work for the crystal structure prediction, and also the scientist in China, we call the Professor Ma Yanming, uses Eclipso to do the structure prediction. And our group, we develop SSW, we call the statistic surface working. And this method is quite simple. From the animation, you just add the Gaussian under the potential, and then you add some energy high energy point, remove the potential, and then you go forward. You can see in a very short time, we can explore the molecular transformations and the solid phase transformations in our, even using the DFT in very short time. And with this data, you can think about we can do a lot of different global optimization. For example, we can overcome this kind of high barrier because you have the bias addition. So this is flowing system is the first time we have tested for our code. We can use our code to add Gaussian to overcome this kind of high barrier for the stone walls reconstruction. And this year, we have adding more, say, functionality in SW, we call the local softening SW. So here is one example. So if we start from a well-known molecule like this kind of butadiene, and can we use computer in no time, in short time, say 10 minutes or 20 minutes, can we identify all these different isomers? So now we think it can be done because you have this kind of local softening SW. It can automatically explore this kind of even to the diradical. And with all this data, you can imagine you put all this data into your training program and you train your potential with all this data. It contains transition state, high energy structures, and eventually this potential will be very good for this kind of molecular findings. And we also tested for the potential surface of this kind of very complex iron carbide system. And we show this kind of potential surface is really complicated. And with our method, we can explore many different minimums. And this is carbon 330 atoms global optimization. You can see the minimum of the potential surface is really complex. And eventually, using the new method, we can identify the onion structure with the 3 cage of these kind of structures. So with all this, I think I do not have many time. I just go quick for these machine learning models. I have mentioned this MBNN architecture, and here I show this kind of generalized graph. So basically, this is CPU model people typically did, and this is GPU model uses the graph MPN network, and we have implemented both. So this is MBN framework, and here is a typical Bella Panello framework for this kind of atomic descriptor and with output for the single atom energy. But with our code, we add actual layer for these many body functions and finally give you total energy. And we also added atomic attention to predict material properties. Here I give you some, I'll just pass all these details. Here is a comparison between our code with the famous, say, different potentials. For example, SOAP. ACSF is coming from the Panello code, and this is global. And you can see this prediction for the energetics of QM9, say, dataset. We achieve a very low record. And you can also compare with a lot of GPU model, which have many parameters, billions of parameters even. Okay, and you can see our model is also very good. Because time limit, I will not go into the detail. We have compared the GPU model with the CPU model for this one. Okay. Our model give you a good extrapolation ability. Okay, I just pass the GPU models. I think just the impression, this one is very good for the prediction. And finally, I give you the scale. So this code can go to many atoms, like 10,000 of atoms. And this GPU model eventually out surpass of CPU model. In our code, we can easily do this kind of larger scale simulation with a good accuracy. You can see we call the SMI simulation to have this kind of oxide growing on these metal particles. It's quite a linear scaling. So finally, I just want to show silver oxide stuff. I just give you a quick pictures. So in this work, we did ethylene oxidation on silver, which is a very famous catalytic system. And we have the silver surfaces using our code with certain coverage and silver coverage. And eventually, we construct a thermodynamic phase diagram, and we find a new phase we call the O5 phase for this silver oxide on these surfaces, and we predict this structure is very good for these reactions. And eventually, we did this kind of selectivity for the kinetics, and finally, we have this reaction to kick off to give our ideal selectivity. And finally, I ask experimentalists to really confirm our theoretical calculations. This is in situ XRD, in situ infrared, and this is reactors, and also other equipment. And finally, this experimental data, and the dotted line is our theoretical data, and experimental data for the infrared, and the theoretical data is also something about here. So finally, I give you some information, say, for this kind of large, very complex system, say silver surface was oxide in situ, and how the reaction occur on the different surfaces now can be studied in our computer, even quite automatically. So the take-home message is the atomic simulation is now really being redefined with all these different, say, machine learning potentials, and also GPU and very powerful hardware platforms. We expect this kind of code can even, say, further expand our scope of atomic simulation, both in generality and in the efficiency. So finally, I will thank my colleagues, and finally, thank you for your attention. Sorry, I didn't keep my time very well.
So if there's just one quick question here in the middle.
Thank you, Professor Liu, for the wonderful talk. I'm a student from Shanghai University, and I'm now working on carbon dioxide reduction. And I both do experiments and also theoretical calculation. And from your talk, I saw a lot of potentials that we can use large-scale simulations for the catalytic process. However, for my field, I work on electric field powered catalysis. Yes. So do you think it is very important to contain those high potential or high current densities into those calculations, rather than those massive numbers of atoms into the system? Yeah. Thank you.
This is a general problem at the stage for many machine learning potentials, but you still can see a lot of publication using machine learning potential in electrocatalysis, because many electrocatalysis actually is the we call the ground state problems. For example, the surface is charged, and the charging the charge will convert into proton or OH onto the surface absorption. So basically, if you consider the in situ coverage or in situ this kind of charge concentration, you can still use this kind of machine learning potential. But it's really difficult to generalize a global or generalized potential for electrochemistry, because different potential have different potential surface, and this is a problem. But it can be done. So that's why this field is not to say used so much for this kind of high current or high voltage electrochemistry.
Okay, thank you.
Yeah.
Okay, so let's thank Professor Liu one more time. And now we will have a 10-minute coffee break. There's coffee available right outside. And I think that Professor Liu has an announcement.
Yeah, so supposed to the library, you know, the stairs. So we just stand on the stairs and have a big group photo. Okay. So before, and then we go to the bus, we go to the band. So make sure, yeah. So go to the photo. Another thing is we have a boat tour tonight. So I won't say this too much. You know what I mean. So basically just a dinner. We have a dinner on the boat. So 2 hours. So roughly I hope we will leave 5:15 and arrive 6:30, and then we start check-in, and then the boat start from 7 until 8:45 or 9 p.m. So roughly 2 hours. It's a round route. So and we have food there. So yeah, I think you get ticket, right? The single one, the band, the ticket with the band. That's your ticket to the boat, right? For the boarding. If you don't have a ticket, please don't, or ask me. Okay. So 2 things. Okay. Of course, you are free. You don't have to go. Okay. You have other plan, but don't miss the boat. Okay. Hello. Yeah.
They give me more time if I think.
30 minutes late, so next speakers are supposed to make sure you finish on time, and so if you can squeeze your talk, it's even better. And we will also squeeze panel discussion in order to leave on time. Okay. So Daniel will continue to chair the next talks.
Okay, our next speaker is Carla Verdi from the University of Queensland. And she's going to be telling us about accurate materials modeling by machine learning and beyond DFT methods, please.
Okay. Hope we're all well caffeinated now. So first of all, thank you to the organizers for the invitation and for putting together such a wonderful conference. I would like to start by acknowledging all the people that I worked with and they were involved at in different parts of this work, in particular Professor Georg Krasse at the University of Vienna, and also he's the head of the VASP software GmbH, as many of you might know. So I will start by simply saying, well, all of you in this room know about what density functional theory is, and pretty much everyone working in the realm of material science and related areas knows about DFT. But of course, DFT is not a silver, the magic bullet, and there's many examples where DFT would fail. For example, here we've got this famous example that is a CO molecule absorbed on a transition metal surface, where DFT will give us the wrong answer about the absorption sites, but also wrong absorption energies and so on. Other examples are, for example, the case of polarions. Polarions are so-called quasi-particles, as physicists like to call things something else, where that form when excess electrons in a material, for example, titanium dioxide, become localized due to the interaction with the lattice phonons. Density functional theory quite famously can't predict very well these polaronic states, or also here, density functional theory struggles at describing water, ice, and water-ice interfaces, and so on. Well, you've already seen today this artistic depiction of the DFT ladder, the ladder of density functional approximations. As you know, we can go up this ladder and have more and more accurate density functional approximations and generalized DFT formalisms. However, these are only going to be useful if they are, sufficiently simple and sufficiently accurate to be usable. Some of the areas where machine learning and AI can help us is, as you heard already before in some of the talks today, are machine learning density functionals, for example, from accurate many-body methods, or machine learning interatomic potentials. Of course, learning can do. These are some of the things I will touch on, and I will touch on some applications of this as well. In particular, I'll be focused on the random phase approximation as our many-body method of choice. For those of you who don't know, the random phase approximation is a many-body theory that combines exact exchange and ring diagrams for the electronic correlation. And the corresponding self-energy is the, let's say, famous GW self-energy, which is used to calculate, for example, accurate band structures and so on, but also is needed for the implementation implementation of analytic RPA forces that are implemented in the VASP code. And we like the RPA because it gives a very good description of, broadly many bond types, and can perform well for both solids and molecules and interfaces between the two. It has a relatively good balance between accuracy and computational effort, although of course the computational cost is much larger than DFT. So if we want to, focus on machine learning interatomic potentials from this random phase approximation, well, of course I don't need to introduce machine learning potentials in for this audience, but the whole idea is that temperature-dependent properties of materials we want to study become accessible via various forms of statistical sampling, and with machine learning potentials we can do that with nearly ab initio accuracy at a fraction of the computational cost. An example here using the machine learning potential implementation in VASP is a calculation of the heat transport in zirconia using Green-Kubo theory, which uses equilibrium molecular dynamics simulations. And in red here we've got the simulated results, which are in satisfactory agreement with experiment and perform much better than empirical classical potentials. But without dwelling too much on this, the whole point is that if you train on DFT, you get at most DFT out for your machine learning potential. And so how do we train machine learning potentials that can achieve accuracy better than DFT without being able to afford the calculation of the training set for these high-level methods? So essentially, the idea is very simple. We exploited the fact that it is much easier to learn the difference between our baseline methods, such as your choice of DFT functional and your higher level many-body method. This, we published this a couple of years ago, but this idea was not new. It was proposed, for example, by von Lindenfeld a few years back, and it's been used and developed in various forms by various other groups. Now, the key thing here is that we built proper machine learning potentials by not simply correcting energies, for example, but also training on forces, which are a bit harder to calculate for many-body methods. And as I mentioned before, we exploited the fact that analytic forces can be calculated at the RPA level in the VASP code. An application that I want to show you involves the calculation of anharmonic lattice dynamics, which is a very, very interesting topic, and a topic that is very relevant for many classes of materials, such as perovskites of different families and so on. And in particular, I focus on a type of perovskite that is essentially the prototypical perovskite, such as strontium titanate, which is quantum paraelectric. It means that there is essentially a ferroelectric instability that classically this material will be predicted to have a ferroelectric ground state, but in practice it is still, the ground state is found to be paraelectric experimentally. How do you see that? You see that, for example, if you measure the dielectric constant, this increases with temperature and then it flattens to a constant value. And this is essentially inversely proportional to the square of this ferroelectric phonon mode. This is quite interesting also for all condensed matter physicists that love diagrams like this. Indeed, strontium titanate is very, very close to it's essentially a critical quantum paraelectric. So it's very close to a critical point that divides ferroelectric and quantum paraelectric phase at 0 temperature. And then there's other materials like potassium tantalate that are indeed farther from this quantum critical point. And the thing is that harmonic lattice dynamics in these materials is for all sorts of physical phenomena such as superconductivity. These materials superconduct with very, very low carrier densities, or a lot of other processes like carrier transport, nonlinear phononics, and so on. And if you look at the potential energy surface as a function of the ferroelectric mode amplitude, you see the typical double well potential, and you see that the depth of this potential is very much dependent on the flavor of DFT that you use, and with the RPA, this is much deeper. So you can set out to calculate the temperature-dependent anharmonic phonons in this material. The way to do that is actually by combining some methods called self-consistent harmonic approximation methods with machine learned potentials. So essentially what you need to do is you need to be able to very efficiently sampling, and in fact the method is called the stochastic self-consistent harmonic approximation. The code is SHA, and you can combine this very well with machine learned potentials to then calculate quite accurately the anharmonic phonons. There are two very important anharmonic phonons in this material. One is the one that drives the antiferrodistortive phase transition at 105 Kelvin, and you see that by following the phonon frequencies as a function of temperature, you see the softening and the temperature of the transition, which is reproduced, of course, with some error by our calculations. And regarding the ferroelectric mode, you see that indeed we can predict a hardening of this soft mode rather than it being unstable, as DFT would say. But you know, it's very off compared to the experiment. The solution came from doing the calculations again with this beyond DFT method, the RPA, which, as you can see, gives this phonons in very good agreement with the experiment. Which again, it's you know, these calculations would be completely unfeasible if we didn't use the help of machine learned potentials. This other related material, potassium titanate, also has a similar physics going on, but it's a bit more simple because this material is always cubic, even at very low temperature. And so it only has the ferroelectric instability, which again is corrected at the anharmonic level, and the temperature-dependent phonons, again calculated with these SHA and machine learned potentials, are in quite nice agreement with the experiment. More importantly, you can also calculate things like the phonon spectral functions, which again need quite high sampling of supercell configurations to get out, and from this you have information on the validity of the quasi-particle picture for the phonon vibrations in the system. Again, let me stress that this phonon harmonicity is really at the basis of superconductivity, carrier transport, and other processes. Now, the process that I want to focus on for this material is actually carrier transport, because if you want to calculate the electron mobility in these materials via standard methods like the Boltzmann transport equation, well, if you do that, you're going to have some trouble if your phonons are strongly anharmonic. So you need a method that is able to include anharmonicity, so-called anharmonic phonon scattering, at least with under certain approximations. So if you run these calculations for both potassium titanate and strontium titanate, well, first of all, let's look at the experiment. Experimentally, the mobilities are quite different, so they're much higher for potassium titanate, but the calculations give us mobilities of very similar values when spin-orbit coupling is not considered. If you consider spin-orbit coupling, then for potassium titanate it increases a little bit. All right, so this calculations are not very good when you compare to experiment, and what we found is that this overestimation of the experimental mobility, which is way larger for strontium titanate, arises from a few different effects that you can disentangle. One is the fact that the structure of strontium titanate is not actually is actually far from the ideal cubic structure that you expect. It is indeed disordered locally. And so again, you need to use supercells that include local disorder in order to capture this effect, which is indeed absent in potassium tartalate. And this means that the electron effective mass is affected and the mobility is affected as well. And then there's additional effects coming from the effective mass normalization due to electron-phonon coupling. And if you consider these effects, you can then recover the experimental ratio of the ATO and STO results, but you still overestimate experimental mobilities by a factor of roughly 3. Now, as also Matthias Scheffler and co-worker recently showed, there is an important breakdown of the quasi-particle picture in these materials, but another effect that is important to account for is poronic effects, as I was mentioning before, which is the fact that electrons can localize or partly localize due to the interaction, due to, again, electron-phonon interaction. So again, here I was showing you some sort of, physical applications of machine learning potentials beyond some of the standard applications that we are used to, in a way that enables calculating electron-phonon interactions at a sort of, including higher level effects such as phonon anharmonicity, in a sort of almost trivial way. And now, small change of gear, and I'll talk about the other topic that I was mentioning, which is machine learning density functionals from the RPA. We already had a bit of introduction, and we dived a bit into the topic already before. So that some key pointers here is that if we can learn a DFT functional from many-body calculations that are, very, very expensive, but we just do it once and we have an accurate density functional, then we should be doing that. And with machine learning, we can actually try and really achieve go beyond the local and semi-local approximations in a sort of systematic way. And the way we tried to machine learn the random phase approximation was by starting from the expression of the exchange correlation energy in the generalized gradient approximation, where you have here an integral. Over here we've got the electron density. We single out the exchange energy density of the homogeneous electron gas, and here we've got the exchange correlation enhancement factor. Right, so for the random phase approximation, we make an ansatz, non-local approximation in this way. So we make the enhancement factor dependent on the electron density in a sphere around each point grid R. Up to a certain cutoff radius, of course. And you can then express this in terms of descriptors. And so essentially the only ingredients are the densities in real space around each grid point. And for the descriptors, we essentially construct them analogously to the 2- and 3-body descriptors in machine learning potentials. So then the other important ingredient is that, like in the case of machine learning potentials, where you learn both energies and forces, to learn the density, the RPA density functional, we try not just on exchange correlation energies, but also on the exchange correlation potential. The recipe for that is given by the so-called optimized effective potential method. You don't need to know much about it, but essentially it allows to map a many-body method to a constant potential. And so this way, by also providing these derivative informations of the exchange correlation energy, we can provide essentially much more information to the machine learning model. And then we use kernel ridge regression to fit both the energies and the potentials. This was an effort that was implemented in VASP. I should remark that, of course, it allows for self-consistent calculations up to a tight convergence. The scaling is similar to DFT. The focus initially was on training for structures containing carbon, oxygen, and hydrogen, including molecules, surfaces, and bulk structures, and a wide variety of bonding types. Now, the bottleneck is that it's promising, but still needs improvement. So this is, I'm just going to go quickly through the examples, but this is phonon dispersions for bulk diamond, where you essentially can see that it reproduces the RPA phonons quite well, and it generalizes well to a large supercell that was not seen in training. And we looked at surface chemistry, so looking at different surfaces, clean, reconstructed, and with hydrogen or oxygen on top, keeping some for validation, and reproducing quite well this surface chemistry. Here's an example of graphite to look really single out van der Waals interactions that are of course key in the random phase approximation. And again, we could reproduce the stacking, both including and not included in training. The sad example is water, where luckily we've got a big screen, so you can see that the sort of reference line here in black, the RPA result, is not, so our MLRPA result in blue does not reproduce this very well. So unfortunately, there are improvements needed in simulating liquid structure here. So I believe I'm at the end of my time, so I'll leave the summary here. But first, again, acknowledging everyone involved in the work, and thanks for listening.
Questions?
So I think this is at least general way to do data learning. So I just curious, this data error in general, is there a kind of systematic reason, or I mean that could be modeled or predict from machine learning model. So that means data learning model can be generalized to any cases or very case dependent?
Yeah, I think it is already being used in a fairly general way. Also, when you just use, for example, a baseline semi-analytical model as a baseline for your potentials and so on before adding the machine learned part. So it can be used for in a very general way.
Yeah, so when you develop the way is general, but once you have a model, can you apply it to other cases without training or again?
Oh, no, not really, no.
Yeah, so that's sort of my concern. Yeah, so
not yet.
Yeah, thank you.
Yeah, great talk. I have a question. So the final part about RPA learning, I think it's it's a great idea. But of course, in RPA, interactions decay polynomially, right? So just having some kind of distance is probably not okay, right? So what are your thoughts on this?
No, that's something that we also pondered for a long time. We're actually surprised that by using actually fairly small cutoff radii, you can actually capture the longer range parts so well. So in the examples that I showed, we were using a cutoff of just a couple of angstrom actually. So that's, I don't really have an answer yet to that. We're still testing because it seems like in the case of water, as you saw, we're not really capturing that. But it seems like by increasing the cutoff radii, we were not actually improving things, either because the complexity increases too much and we need more data and so on, or because the cutoff is not the issue.
Yeah, I think you can mimic van der Waals interactions by some electrostatic-like attraction in a functional, right?
Yeah.
And that's like Anatol von Lilienfeld had this approach to change zero potentials that mimic van der Waals interactions. I think this is what you are doing with your functional, right? That if you have a mixture between electrostatics and van der Waals interactions, so correlation and electrostatics, I think this will be much harder to do. You need a polynomial decay, right? Essentially.
It could be interesting to explore the long-range descriptors as well to solve the problem.
Yeah.
Okay, we need to move forward, so let's thank Professor Verdi again. And our next speaker, I'm sorry if I don't get it quite right, Li Shui?
Yeah.
Li Shui Xing. Thank you. So Dr. Chung from Microsoft Research AI for Science Lab in Berlin. Recent advances in deep QMC developments and its molecular property calculations.
Hello. Thanks a lot for introduction and thanks a lot for the invitation. And I'm Sherry from Microsoft Research AI for Science Lab. And today I will try to introduce some superficial deep QMC. And mostly I have used the deep QMC wave function to continue calculating some other properties that might be very interesting. And this is today's outline. So the paper for today's content is recently released on archive, and if you have some time, please take a read. And that's really helpful to further understand the details about the methodologies that we're introducing today. So before introducing the deep QMC, I would like to first give a very big overview on the ab initio electronic structure calculation. And we have already covered a lot of the DFT-related contents today. And the previous speaker have already said, okay, DFT is not really satisfactory, so not all satisfactory. So that's why sometimes we need another type of theory called wave function theory. And usually people will think about wave function theory from these three, MPT, which is the perturbation theory, cup cluster, CCSD, and the CCSD princess T. And usually people will refer CCSD princess T as the gold standard for computational chemistry. So basically, if you're reaching this accuracy, you're terrific. But today, actually, we could also see some issues about cup cluster, and especially this gold standard. So for some hard problems like multi-reference systems, cup cluster will also fail. So then, there is another type of the wave function called quantum Monte Carlo. So it is using a totally different strategy to do the wave function. So basically, it's using the Monte Carlo sampling to sample the wave function and find the wave function. And actually, I also missed real history about the FSE electronic structure, and the quantum Monte Carlo itself has already been proposed for many years. But recently, people starting thinking about how to do it with machine learning. And of course, there are other fields that people have already mentioned today. For example, machine learning force field, machine learning DFT function layer, and of course, very recently is the deep QMC. And just several days ago, David Powell group published an exciting state paper on science on using deep QMC. And of course, the story of the deep QMC and QMC will continue. And to start today's talk, I want to give a very big overview on what is actually quantum Monte Carlo is doing. And we are restricting us to variation of quantum Monte Carlo, so there is no diffusion Monte Carlo discussed today. So don't get confused. Sharding the Cornerstone equation, that's another story. But for this electronic structure problem, Schrödinger equation, we could also equivalently change it to a variational principal form of the Schrödinger equation by minimizing this really quotient. And then people come up with this variational quantum Monte Carlo idea to the ground state and the ground state energy. So our goal is that we want to minimize a wave function that's determined by your theta parameters. Well, this is a parameterized wave function that could minimize your evaluated energy. So this will be a ground state energy, and this will be a ground state wave function. So the loss function, because this is a variational principal problem, then the loss function is naturally will be your energy. So you are minimizing the energy evaluating on the current wave function. And this is the equation, and I will come back to it a little bit later. And this wave function beside, it is a parameterized wave function. So basically saying that you are having some parameter theta that on your location, these x1 to x3 are the location of your electrons or electron coordinates. And of course, if you're doing it in a deep learning framework, then this will be a neural net. And of course, if you don't want to do deep learning, that's also fine. You can use some other parameterized functions, just not neural network. It will also work. And then let's come back to a little bit to the loss function part. So our goal is to calculate this minimize this during our minimization, and which is all our loss. Then how to do this calculation? So what we are doing is using a Monte Carlo sampling to sample the electron location from the percent theta x squared. And also then we also will evaluate a term called the local energy, which is purely determined by the current Hamiltonian and the current wave function. And so basically this is saying that given a certain set of parameters and the wave function form, we could evaluate the current energies, which is a function of theta. And then by minimizing this energy, we could find the optimal theta. And like I mentioned, recently there is a paper published on excited state. So everything we discuss here is ground state setup, right? So how to extend these two excited states? Basically, you need to add another term, which is the overlap term between the two states. And what you want to do is that during your minimization problem, you want to both minimize your energy and also minimize your overlap to make sure your state has zero overlaps. Say I have a ground state, first excitation, they should be orthogonal, they should have zero overlap. And it's a kind of control term alpha to make sure that you could do a proper minimization, because when your Sij is closing to zero, you can think about this term will be very different. So you want to using this alpha control optimization. And then, like I said, this is actually a traditional QMC setup. So what is special in the deep QMC? The question will come back to practice parameterized wave function. And there are two main principles we want to follow. First is that we want to have very good expression of the physical wave function. So that's a term in neural network called expressivity. So how well, what's the ability of your neural network to describe the physical system. And also we want to have a pretty low computational cost, because we don't really want to do a lot of sampling. Otherwise, it probably was better to do just a couple clustering, or maybe MRCI, or maybe even SHCI DMRG. So then we have come up with the basic idea that we want to do some correction on top of the mean field rival theory. And the point we start from is a Hartree-Fock. So what we do is that we construct our wave function from the Hartree-Fock theta determinant, and then we build on top of it by doing some by correcting the constellation, by including the constellation explicitly in our neural network construction. And we call this just the backfill wave function. And this is the common format of it, of the gestural backflow wave function. And in the deep QMC, we will further develop design the two components, this gestural backflow wave function in this term. So this first term is still the gestural term, and then we split up the determinant into the many-body octal term and also the envelope term. And this just want to make sure everyone understand that we are still at initial calculation. There is no real big data learning because we follow the variational principle. And during this development, we realized that for this many-body orbital term, what we want to do is we need to use some equivariant graph neural network to design it, because we want to realize these two properties. The first one is E3 equivariance, and the second one is permutational invariance. And here, due to our limited time, I will just list if you have some interest, you could take a further read what is E3N and what is graph convolution layer. And we also have some parameters in our value to help us to learn behavior, basically the wave function decay behavior. So we know it should be the exponential decay, and we just definitely have some parameter inside of it to learn this decay. And we also have some control condition on condition. You have a just condition, and there is also some parameter inside of it. So the multiples you can find the data for a real paper from Herman as well, and Nature Review Chemistry, because today we are now really only introducing DPMC. So DPMC has recently become more and more popular and powerful. Here I'm just showing some of the applications, and this control is just a visualization of when your electron is wandering around during your MCMC sampling, and this is a lithium hydride system. And during these years, we actually have pretty good progress in this field. So paper from DeepMind by David Parker on the excited state, and this is the figure. And we can also solve the band breaking problems very long time ago. And this is another individual project by my boss, Frank Moore, in his university, published last year on excited state. And there are also some trials to calculate some tubular conductivity and its laser transition. And there are also some, other chemistries involved, and people some backgrounds calculating simple materials using DPMC, which is more related to this topic. And of course, there are more possible future applications because PMC and DPMC is providing general solution to Schrödinger equation. We are not limited by single reference or multi-reference. So we could do some superconductivity calculations. We probably can also do some physicochemistry and quantum dynamics. These are all possible future applications. However, DPMC, while it is not as popular as machine learning for DFT or machine learning for field, there is definitely issues inside of the DPMC. The first one is about the cost. So although we could just kind of simplify the NP-hard Schrödinger equation solution problem to actually, it is not a linear, not a quadratic square with n cubic in the performance about the DPMC, but this is still very expensive, not as a competitive as other methods. So that's why there are two developments recently focusing on two sets. One is geometric transferability, so basically reframe the DPMC as a machine learning software problem that I'm learning entails potential instead of just one point at a time. And the second development is called Laplacian. This is more deep learning set, so how we could compute everything more efficiently. And also the second issue of DPMC is that we usually checking on energies instead of, wave function is something that when you calculate it, you should be able to evaluate everything. So there should be more efforts developing on how to do more developing on how to calculate properties on top of the DPMC wave functions. And definitely there are some of them. Previously, this is by Ji Chen from Peking University. They did some homogeneous force estimator based on the DPMC wave function. And today, we are also doing something similar. We focus on evaluation on top of a converged DPMC wave function to fully get accurate properties. And the first property we are focusing on is about density. And of course, density is a lot of people are saying here might care more because if you're working on DFT, density is very important. Of course, we also notice some potential issues in the current densities using traditional wave function theory, including for CI. That because you are using Gaussian basis densities, you have to use Gaussian basis densities for the conventional calculations in the wave function theory. So you will have two issues. The first one is about the incorrect physical limit, and more specifically on the exponential decay, basically the tails of your wave function, and function basically when you're having everything on your core. And the second issue is about the basis set completeness. So currently the basis set we are using maybe STO3G, CCPV-TZ. These are just incomplete basis. So if you want to use something complete, you need to use the CBS limit. This is usually challenging too. And usually you can correct on this problem usually on energy. So our goal then becomes to how we could get high quality and physical real space density from the general wave functions. So I want to mention that our method is okay for general wave functions, not only for deep QMC wave functions, but because like Hartree-Fock, you can directly extract densities. There is no need for you to use this method. And then we can say, more realistic or more practical expression is a general variational quantum Monte Carlo. Currently, people are using DMC or FAQMC, which is the second type. Oh, only 1 minute? Oh, okay. So I have very limited time. So I want to quickly skim our method on the neural electron real space density. So this is our target that we have our electron density. This is what we are evaluating. And from the definition, we are trying to evaluating a high dimensional integral, which is very expensive. And naively, what you can do is you can do some quick Monte Carlo sampling and get the electron position and do histogram, and then you get a waveform, you get a density. But their choice we have, which is fit the density as a function. So this is the overview of our strategy. That the first idea we have is that we directly parameterize this function as a neural network and run the maximum likelihood estimation to minimize the negative log likelihood. But we have some normalization issues because your wave function have some missing or unknown factor on the normalization factor. And the second idea we come up with is called energy-based model plus the score matching. This is a very traditional deep learning approach that we could skip the normalization issue. However, doing the second idea, we can get almost everything correct except the distant systems because the score matching method is hard to detect to model the two distributions that is far away. Because when you do score matching, you need to sample the points that connect the two distributions together. But because they are too distant, too far away from each other, so it is hard for you to do this sampling. And finally, we come to the final solution is we beyond the score matching, we also add something called the noise contamination, called NCE. It is a way to help you to make sure you can feel another distribution about your density. So because I'm running out of time, so I will skip all the details. If you have interest, you can read our paper. Most of them are pretty machine learning to be honest. So I will just directly go to the performance of our model. So the first thing we do is we want to check our density on the atom. We have very good references, even from the experimental data and also from some traditional calculations. And we got everything correct. And also the second thing we check is about the physical limit, because that's the reason why we claim we are even better than FuCI. So here we compare with FuCI with OGCCPVQZ on a very small system. And we find that we have exact clasp condition, but the FuCI cannot do it because it's still a not complete basis set. A more severe issue is about the tail that we also compare with the FuCI data. We find that usually if you think the tail, it should be plateau instead of have a bump. We are a plateau, but FUCI is not a plateau. So we are better than FUCI in terms of the physical limit. And we have also a terrific overall quality in terms of the density calculation. We also test on some other properties. This is the effective potential calculation. And we see that for the FUCI, there are some numerical instability, but we are completely smooth. And here is also a dipole moment of the lithium hydride dissociation. We also nailed down this problem. The final results that we got track is a Hellman-Feynman force, and we test on the dissociation curves of these three systems and using different estimators. So there are some reference from the energy-based estimator, and we also have some results from our estimator. It's called NERD estimator. And if you are interested in the full derivations, you can find it from our paper supplemental. The final thing is about the scalability, that we find actually we can do H4, which is very easy, and we can also do benzene. So we can also do system, but benzene is pretty good for us to check because it's completely symmetric. So we check on a lot of other properties about the density symmetry and also the dipole moments, and verified we have very, very good density. And I want to thank my collaborators, the QMC team, and also our leader from the MSRE Process Lab, and my colleague Hongxia will probably introduce more about our org. And we want to introduce our Deep QMC repo. And if you're interested in this very accurate, very fundamental method, you can go to Deep QMC, and we have a nice tutorial to tell you how to run the Deep QMC. And we will release more and more developments, especially large models. And please stay tuned. Thank you.
Thank you. Okay, maybe one quick question.
Thank you for the. I want to ask, how does the deep QMC compare to other machine learning wave functions like Fermi net, what's a former, for example, in terms of variational free energy, especially for the challenging systems like dissociation of nitrogen?
Both of the methods you mentioned are deep QMC. So deep QMC currently including FermiNet, Cyformer, PolyNet, these are all deep QMC.
But they are of different deep learning architectures.
Yeah.
Compared
different architectures, but they are always deep QMC. They are also deep QMC.
Well, I want to understand the performance difference between these different kind of deep learning architectures.
Oh, okay. So there are, well, this is pretty technical. So there are several different categories. Say, Cyformer is a transformer-based architecture. So currently, we think Cyformer has the best performance, even better than FermiNet. FermiNet and PolyNet are modern, but currently, I think in this paper, we're using Cyformer because Cyformer is the best. And it's mostly recently released.
Okay, thank you.
Okay, let's thank our speaker one more time. Yep. Okay, and our next speaker is Hongxia Hao, also from the Microsoft Research AI for Science Lab, AI for materials from simulation to generation.
So thank you very much for the introduction, and thank you very much for the opportunity for me to present our work here. I am also one senior researcher from Microsoft Research AI for Science. My talk is mainly about, say, the AI opportunities brings to material science design from simulation to generations. Before our discussion about materials, I will introduce a little bit about our org. So Microsoft Research announced a new organization, AI for Science, about 2 years ago. It's a global team composed of machine learning, chemistry, physics, biology, and engineering experts working together to tackle some really important society challenges. Currently, we have China, UK, Netherlands, Germany, and USA. So if you're interested in it, please find more from this website or talk to me. I would say for a scientific world, it's really a multi-skill properties. And today, our talk, so it's ranging from particle physics to astrophysics. And for this talk, I'm mainly focusing on the atomistic world and mainly focusing on these crystals. So the laser is not working well. Let's just see the screen. For really a materials design problem, traditionally when we design materials, experimental trial and error fashions, it usually takes 10 years and also millions of dollars for only one single material to go from design to market. And every material will bring a revolutionary progress. So why this takes so long? We think not only in the material design process, but also when you go to the lab, you need to think about more factors regarding the synthetic conditions, including pressure, temperature, etc. And that makes it very challenging. And the current method is hard to optimize that part efficiently. So ultimately, how we do a materials design are basically in two lines. We call it forward procedure materials candidates for you to quickly predict the materials properties at real conditions. Another way thinking back is for materials that doesn't exist on the market, you really want to have some specific properties. You want to design more candidates for you to explore to provide you more candidates. And what we do currently are focusing on these two directions, not only on AI-powered predictive modeling, but also backwards for generative AI for materials generations. The first part is focusing on MetaSim, our recent work developing an atomistic deep learning model across elements, temperatures, and pressures. As I mentioned before, when we focus on the material space, we are not focusing on the composition space, but also thinking about the real-world conditions, including, let's say, temperatures and pressures. And this brings us more about conformation space. So mainly the open-sourced data set and also the previous called universal machine learning potentials, mainly focusing on these ground state structures, is mainly on university on composition space, but less on temperature and pressure space. So we say there is a 0K curse. So that we think that's why when you do material synthesis, it's usually for you have a very high failure risk because you didn't consider those parameters. And also there are many property predictions that give you wrong answers because of lacking of that. Then for us, we really want to bring all the factors together. The way that we did is just thinking about use open sampling technique to make sure you cover the conformation space and also the composition as possible. And because all the labels show results for reproduce of this figure, it takes more than 10 years experimental work plus theoretical simulations. Here we can recover for this plot is just using 30 minutes. And you can see the blue curve is line of the face. To complex systems, that we cannot make sure that we covered all the there are a lot of simulations that requires maybe millions of atom simulation for molecular dynamics. What we can achieve, I will show in the following that we can do millions of atom simulations with guaranteed DFT accuracy, but it's only a few GPUs. Traditionally, when we think about model, that we evaluate its accuracy and uncertainty, uncertainty. If it's with high uncertainty, we will do active learning. However, for such big systems, it's hard for us to label using DFT label anymore. So what we think about the strategy is to do a substructure embedding by looking. In principle, these models are mainly kind of describing the local environment. So as long as you cover enough local environment, you are good to go. And this is the same idea applied here. By cropping out this local environment with a much smaller size and do optimization for these uncertainties, we achieved the in-distribution estimation of the substructures, and that helps us to increase the efficiency dramatically. Here is the example showing a 1 million atom simulation of the lithium melting initiates by grain boundaries, and the system size is at million level, but we can cover this 20 picosecond simulation, really see the melting just using one GPU for only about 4 days. so one A100 GPUs. So another example, maybe more interesting you, is to really do a real-time simulation of real-world problem. Let's say it's Haber-Bosch reaction, catalysis process. For our simulations, by using the same strategy, we can simulate the process on such these nanoparticles, but with system size over 2,000 atoms on only a single 100 GPU with 24 CPU cores in 3 days to finish the simulation for tens of picoseconds. As you can see that if we didn't use our strategies to really refill those local environment and re-optimize your model performance, just run from the scratch, that you cannot stabilize the nanoparticles at all. Okay. For our model, for this strategy, it's not it can perform linear scaling because of the strategy for just the local substructure compared to traditional DFT methods, and also because the labeling for this local structure can be parallelized. So as long as you have a lot of CPU nodes, you can finish all the simulations from 30 days to 3 days if you have enough of resource. Another one is, so our strategy provided before is more a bottom-up approach. Basically, you form a structure and go through a neural network to mimic the fundamental interactions to help you predict all the properties. What if the property is really hard to compute from this real bottom energy force? So what our strategy is, we can do a correlation between the structures and the properties. It's called end-to-end models. So however, if the model is small, the parameters are little, it's fast, but because it's lack of data, it also means it's lack of generalizability. And for our model, we just have a quick benchmark on the MathBench benchmark. We can see and easily we can outperform all of the previous SOTA for us. I want to say that we are not meant to do all the comparisons with SOTAs and benchmarks, but it's just trying to say that show the power of our model. Sure. And very quickly to summarize, go to the next topic is, so I described the forward procedure, and there's another property guided inverse design for materials generations. And here, basically, it means the material sense currently the space is large, but not that large. If you have a much wider space for you to explore, in traditional machine learning field, there is diffusion techniques to help you generate a lot of figures with different kind of images, like girls, men, smiling, angry, whatever. So we take the similar kind of spirit to do materials generation based on some specific properties. One example is our model called distributional graphomer that can provide you a Boltzmann distribution for materials with specific properties. Let's say if you define the material that you want to find to be band gap to be 4 EV, that you can exactly find some material to be diamond. If you define some band gap to be 2 EV, this materials founded has been verified by DFT that it is 2 EV. And another model that we define specifics for materials is called metagen, that is taking advantage of the chemical information and the space group, and also type the properties. It helps you define the materials. So looking into the future, think about in your mind, what would you like to achieve? We will say, hey, design me some material to fit my whatever needs. We hope the whole procedure will help you find and design whatever you like. And we hope this will come true very soon. And this is pretty much my end of my talk, and thank you very much for your attention. I'm very happy to take any questions.
Questions for Hongxia? Yes, Mohammed.
Hi, Mohammad Khatamirat from Technical University of Berlin. Thanks for this interesting presentation. You showed the binary phase diagrams and the thermodynamic stability of manganese oxide. Do you have examples where you extend this workflow to other binary systems? And the follow-up question would be, would you say that the current workflow is in a state where any non-expert can come in, access, and then within 30 minutes, as you showed in the slide, get a phase diagram for any two elements of the periodic table?
So currently, we are trying to benchmark our, at least for the free energy, for various type of materials, as long as you have some experimental data. And we have a benchmark. I didn't show it here because of time limitations, but we did quite well, and I should say super well compared to DFT results. That means we have the capability to reproduce the phase diagram in principle for kind of materials that you can think of. We tried a few other materials that kind of can do roughly well. We haven't done for kind of tons of them because of the resources and times, but currently we at least show the capability that we have.
So that means a grain of experimental validation is still needed in the work.
Yes.
Thanks a lot.
Yeah, thanks for that very impressive talk. So if I understand this right, what you've done is develop a general purpose machine learning force field that spans a large number of elements across the periodic table, like 80 or something like that. Is that correct?
Yeah.
So can you comment about the training data, that the size expanse, chemical space of the training data that you used, and more importantly, the computing resources that you needed to train this? You showed some timing for inference, but you didn't say much about the timing for the training.
Yeah. Okay, so I basically show the strategy how we generate the data. We're starting from the ground state geometry, let's say from materials project, and also from random structure search, etc. These are mainly kind of ground state structures, and then you run molecular dynamics at finite temperature and pressures. And temperature can go from 0 to 5,000 K. Pressure can go from 0 to 1,000 gigapascals. We try to reproduce as wide distribution as for conformation as possible. Given that, we have the strategy to develop, etc., how we do efficiently. After that, then it's kind of 70 mainly, DFT calculations at PBE level theory, and we use WASP software for the current, and there is an estimation of how much you could take. Like,
yeah, how about the computational resources for training?
For training, I think it's not a very big problem for us. As long as you have a few tens of GPUs, that should be fun. Yeah.
Okay, I think we're actually going to have to stop discussion because we're right on time, only over by 40 minutes. So let's thank all the speakers of this session one more time.
So next we'll enter into the panel discussion. So please come in. So please show the panelist. And Rika will be in charge of the discussion.
7 chairs. 7. Yeah, I don't need to sit down.
First 10 minutes, yeah, but finish in 30 minutes.
You want me to finish in 30 minutes?
Yeah, 30 minutes. Okay.
A 30-minute panel instead of an hour?
Yeah.
Okay. Well, that's different. Well, hello? Yeah, apparently we've only got 30 minutes for the panel discussion instead of an hour, so we're going to have to do this very, very quickly.
Yeah, so please
come to the...
find your seat. Yeah, there's a name there.
So,
you want me to finish it?
Yeah, so please finish in
Thank you very
30
much.
minutes.
So basically, yes, I'm Rika Kobayashi from ANU. I'm very pleased to be hosting this panel discussion. Without further ado, I will introduce to you my panel. This is Professor Hong Wang from Shanghai Jiangtong University, Rampi Ramprasad, Matthias Scheffler, Professor Tongyi Zhang, Shanghai University, Daniel Crawford, Professor Turab Lukman, and Hongsha Hao, who we've just heard from. So please welcome the panel. So because we've got to do this quickly, I'm just going to throw questions to various people, and if we have time for more people to answer, that would be great. But to start off, a very beginner question, which I will put to Professor Chang Tongyi and also, I think, Professor Lukman. So the first question is, ignoring the Nobel Prize for the moment, what do you think has been the biggest advance that machine learning and AI has made to chemistry and material science? Professor Chang.
Maybe you go first. You see. Yeah.
Oh, okay. Well, Professor.
I mentioned that both
Yeah.
are
Okay.
named. Okay. Please.
Yeah. Well, with Professor Lukman, I particularly was interested in your perspectives from the excitement generated by autonomous labs. So I was wondering if you thought that was a success, but please go.
So there's a lot of work being done currently, of course, in numerous labs in China as well as in Canada and in other places that are trying to sort of these are sort of self-driving labs. In other words, how can you basically get the human out of the loop? In other words, can I come up with an experimental synthesis capability that basically takes the human out of the loop, that does synthesis, that does characterization, and that actually also does design. And so I know of several labs that are trying to do alloys, that are trying to do ceramics, ferroelectrics, for example. In Beijing at USDB, Professor Bai is doing a very nice setup where he's essentially designing ferroelectrics, taking the powders, doing the mixing, the calcining, doing the characterization, and then coming back. And so that's one area that is really a cutting edge area, and it's sort of driven by this desire to do autonomous systems. So that's one thing that's on the horizon, and it remains to be seen. How can we actually design novel materials, especially materials that are not typically captured by the training data? I mean, that's one of the challenges. You can always try and make predictions of materials families that are in some sense represented in the training data, but how do you go out of the scope of the training data? In other words, that brings in aspects of generative AI. So that's one of the big challenges that I see going beyond, especially in the sort of wider material science. And of course, we've heard several things related to how do you come up with better models, effectively surrogate models. These are what I call surrogate models for first principles calculations. And you've heard a lot today about that.
So we might come back to the end for that bit to follow up because we're running short. So Professor Tongyi, what do you think has been a good success?
Yeah. Very happy. Okay. To talk about that. It's my personal opinion. Okay. In my personal opinion, I think I say to develop AI for materials, they need two. Basically, it's a foundation. One is just Professor Lukman mentioned that we need an AI lab. We have to do experiment. Okay. Another, I call it a soft. AI lab is experiment parts. I call it a hard. The soft part is a computation. Okay. The computation, the AI in both sides, okay, the both foundation are developed very, very fast. Very, very fast. For those parts, for those say soft parts, computation, we are covered from the further principal calculation, MD simulation, excellent work, and our Microsoft, okay, AI for science. But your AI at the moment, I know that we cannot consider any defects, even though for polymer, we also have defects. It's not so perfect. For perfect crystal, you may can do is a lot of things. But I put a dislocation here, put a different green boundary, green side here, a lot of defects. Then it's really, I talk to these people, they're always on the way to get, we call those equation, the state equation. Or in mechanics community, we call continuing equation. We need that. That's not so easy, okay? The whole life you have to do that. So I think we have a great achievement where it's a work together. This is a conference. It's a more emphasis on this competition. On in my personal word, it's on the soft parts. We have to make it stronger and stronger. Okay, so make it stronger. Then on the other side, we have to make those hard part foundation, the AI lab. Okay, to make it, I'm in Shanghai University and also in Hong Kong University, Guangzhou, in both sides. Then on the other side, we have to make those hard part foundation, the AI lab. Okay, to make it, I'm in Shanghai University and also in Hong Kong University, Guangzhou. In both sides, I'm going to build up AI lab. Okay, so Liu Yi probably will show all those.
This is, I mean, we know that AI, ML is being driven by big data. We don't do big data so well. How do we ensure integrity, accessibility of data?
Well, if I want to say one word, is that's the standard. Currently the data, how we collected the data, how we accumulate the data is basically the data is the byproduct of the research activities, and everyone does it, but the data is only served for their own purpose in a relatively narrow area. And but nowadays, AI has been the main force, or more and more become the main force in the research, in the material development, and we need a more general data, and that will require everybody when they doing their data, and they have to follow certain rules. So the data can be easily transferred, can be easily shared, can be easily combined into a big data set. And that will be a fortunate thing for the AI, for a short answer. Yeah.
So who sets the rules?
Who sets the rules? Should be everybody. And I think the rules have to be, have a thorough survey to the community, not one but just collecting everybody's idea, then it's going to be out of focus. But if just following few people's rule, that's going to be also some problem that may not seeing everything all the way or all together. Yeah.
So at this point, this is why I want to throw to Hongsha, because we were talking about industry and sharing data. So please, Hongsha, please give us your perspective from industry.
Sure. Thank you. I will have some personal opinions, but I will say this is really not representing my company. I'm just a researcher from this field. So we all realize the data is very important, and we have the desire to really, for example, validate, benchmark, and evaluate our data at various aspects. So currently the data is very limited. It's defined by some minor groups. It's the community who are responsible to build up this community to see some standards. Let's say if there is a publisher like Materials Project, like PDB Bank, they will define some standards for us, for everyone to follow. So it will create some driving force to follow that strategy, to create some data to be accessible, maybe reusable, reproducible, etc. Another point about data that I really want to mention is about the benchmark data. Currently, even though I show some data to benchmark with, but we are sure that data cannot represent your quality of your model. For example, evaluation of just the energy and false error MAEs is definitely not enough for you to do really something trustworthy and helpful for real world applications. So for us, as a company, we really focus on solving real world challenges to prove that your model is really helpful.